Now, how do we convert our equations into a logic circuit which can be later on usable in our design? So that is our uh, next topic. So looking back into our previous example, so the output x is equal to c d complement plus a complement b plus a d complement. So how do we create a logic symbol or a logic diagram for this equation? So here now we will be using what we have learned in our previous lessons about logic gates. When we say multiplication or the product of two terms, we are actually using the logic and addition means logic or. So in this example, we will have input, three inputs. So we have input A, we have input B, we have input C, and we will have input D. So we will have three line diagrams for this one. We have four line diagrams for these four inputs. So if you have noticed in our first term, C is multiplied to D. So we have AND. So our symbol for AND is this one. So our input C is multiplied to input D. But take note that our input D is complemented. So that's why it is to complement, we have this not symbol before the input. So D is knotted, or i-enlarge ko lang ha. Not is the symbol. So this is a knot. So let me just redraw. So it is inverted before it is placed in the input of our AND. The second is A and B. So A is ANDed to B, so we will again draw. So we have A. Again, if you will look at the example, A is complemented, so we will have a NOT gate before it will proceed to the end. So we have here A, then inverted, and we have the B. So we have here the B. And the third term, we have A and D. It is also ANDed. So we have A and D. And all of the three terms are added. So we will have the 4. Or so we will have a big, this is our output X. So the three inputs are 4. So this is the logic diagram for C times D complement plus A complement B plus A D. So this is the logic circuit for, yeah, this is the circuit diagram for the equation of our X. Okay, now to fully appreciate the importance of KMAP, let's go to the real world problem example for uh, the utilization of our KMAP. So in this problem, you are asked to design an alarm system for a garage. So sensors are installed in the door of the garage and the window to detect if it is open or closed. A light sensor is also installed inside if it is to determine if it is dark or the garage is lighted. So the alarm shall sound if the alarm switch is on, the garage door or window is open, and the room is dark. Please take note that in this example, uh, the conditions to determine if the alarm will sound if all of the conditions are met. That is, the alarm will sound only if the switch is on, the garage door is or the window is open, and the room is dark. All right. So first, we will be assigning a logic for each of the sensors or each of the inputs needed for the design. So first, we have the alarm. So alarm will be, one will be for on, and of course, zero for. Next, we will have the uh, door of the garage, or let's say it is the, so in order for the Anna, we will change, can I change the, instead of door, I'll just change this into gate so that I could, so we will not have a duplicate assignment of Anna. So again, our next input will be the gate of the garage. One will be if the gate will be open, and zero if it is off. And then we will have the window. We'll assign one if it is also open, and zero if it is off. And lastly, we have the sensor for the dark. One if it is dark, and it is zero for light. Or shall I assign this into ano na lang? Uh, this is a photo sensor or the light sensor. So those are my assignments. So what will I do next? So next is I will be drawing the uh, truth table for the three inputs. What are for the four inputs? A, G, W, P. So we will have inputs A, we have inputs G for the gate, W for the window, and P for the photosensor. Then I will have my output here. So what are the 0, 0, 0, 0, 0, 1, 0, 1, 0, I 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, and we have 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and 1, 1, 1, 1. So this is our truth table for our inputs. Now, according to the problem, the alarm will sound only if first condition is the alarm is on. The alarm is on. Of course, our alarm will not turn on or will not sound if the switch in the alarm is off. So one of the conditions is that the alarm is on. So take note. So all the inputs here indicating that the alarm is off, the output will be 0 because our initial condition says that all in order for the alarm to trigger, all of the alarm input shall be on or the alarm switch should be on. Now, particularly on the second condition, it is indicated there that the second condition states that and therefore the first condition and the second condition should be satisfied. So the garage gate and take note of the conjunction or the garage gate or the window is open. So either the gate or the window is open and the alarm is on. So in these conditions, where the gate, where the window and the gate is open, the alarm should be, uh, the output should be triggered. So what are those conditions? Here, this condition, the gate will, the alarm will open. And in these conditions, because the gate, this condition also the window is open. And in these conditions, the gate will also open. But should I already write the output for those conditions? So meaning in these two conditions here, both gate and the window is closed. So automatic the output is 0. So going back to the problem, so take note here, we have and and. So that means the conditions in order for the conditions to be satisfied, all of the three conditions, this is condition 1, this is condition 2, and the condition 3 must be complied. So going back here. So here, although the alarm is on and the window is open, but our photoresistor or our light resistor is 0. And it is mentioned here that the alarm will only open if the room is dark. And we said that the room is dark if the value of your P is 1. So here, since the value of our P here is 0, so it will not light. So here, the window is open and our P or the photoresistor is 1 or it is dark. So we will have an output here of 1. Here, the gate is open, yes, but the photoresistor is also 0 or lighted. So it will not open because our condition says that it should be dark or 1. Here, the gate is open and the photoresistor is dark, so the output is 1. Here, the gate is open, yes, the window is open, yes, but the photoresistor is 0, so the output here is 0. So in this condition, all the conditions are met. The output is 1. Now, we already have the truth table. Now let's convert that into our K-map. So we have here the AG and we have here the W. We have here 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. So it will have the output of 1 of the following inputs. 1, 0, 1, 1. So where's 1, 0, 1, 1 here? And another one is 1, 1, 0, 1, 1, 1, 0, 1. And the other one is 1, 1, 1, 1. And all the rest are 0. Applying our K-map, so we will have this grouping. We only have two groupings. And the output, let's say this is our output Y. Our output is just equal to, here, how do we write our, here, our A and our G is not changing. So we have AG, and since it is 1, so it's true form. How about our WP? Our W is from 0 to 1, changing. Our P is 1, 1, so we have AG and next plus. How about in this grouping? So we have our A is not changing, so we still have A. Our G is changing from 1 to 0, so we will not consider that one. And our WP is not changing because they are on the same column. So our simplified equation for the output is AGP plus AWP. How do we convert that equation into a schematic diagram or a logical schematic diagram? So again, we will have these three input A, G, W, and P. So we have here the lines or the input lines. Next, what is our equation? we have A, G, and P. So we have that is ANDed. So we will write A and symbol. Di ko paano gawin ka and so first is A, G, and P. We have input A, we have input G, and we have input P. AGP, and we have also AWP. We have A, W, and P. So this two is added. Then we have the for symbol. This is our output Y. So Y is equal to AGP plus AWP. So that is how we converted our uh, equation into our logic diagram or logic symbol diagram. So here, I hope you have appreciated the importance of mapping, especially in solving for real life problems and real life translated into real life situations. So later on, you can use this one in your design projects, uh, especially when you go to your microcontrollers. You will be utilizing different gates, logic gates, in uh, different situations. So next we have here the don't care conditions. So sometimes, so sometimes there are conditions that utilize don't cares. So some of the midterms may never occur or it may not matter whatever happens, what happens if they do so. So we call that one, those conditions as don't care. Kung sa Barahara, they are the joker or sometimes tawag ka na, ang organic. So ano, sa mga card games we call that the wild cards. So when we say wild cards or the joker, you can use them as replacement to whatever one or zero during the minimization. So like in this example, uh, here in this grouping we have here, we can group this one and consider x as one in grouping because x is a part of the don't care in the given situation. So we can consider this x as one and be counted as a group to form a group of four. So that is the use of the don't care. Then we have the exclusive or the exclusive nor. So again, exclusive or and the exclusive nor. So you are just given here the truth table for the exclusive or and the exclusive nor. So the exclusive or produces high output whenever two inputs are at opposite levels. And the exclusive nor naman if it produces a high output whenever the two inputs are the same level. So still it is part of the logic gates that we have uh, discussed earlier. So anyway, I have included in our uh, what you call in our notes the list of the logic gates we have, that we commonly use. Let me just open it first. So here, anyway, in our Escuela, it is found here on the TTL Logic Family IC. And when you open it, it will look like this one. So if later on, if you will be using this TTL Logic Gate IC in your project, you will be looking for this number. For example, you will be needing a quad 2 input and gate. So the number of the IC is 7408. So quad because in one IC you will see four different AND gates. So AND gate 1, AND gate number 2, AND gate number 3, and gate number 4. So here, please take note that in the IC, here, that is the pin, this is the pin configuration. So pin 1 is the input 1, pin 2 becomes the input number 2, and pin 3 is the output. So pin 4, pin 5, the output is 6. Then the same here, pin 8, pin 9, pin 8 is the output, pin 9 and pin 10 is the input, and here pin 11, pin 12, and pin 13 is the input. So in every IC, we will find here the VCC and the ground. That is your supply. That is where you put your supply for your IC. So para magana ang IC, you need to put a supply to the IC. Usually 5 volts, and here you place that into the ground. So before wiring an IC, so please take note of the pin configuration. You need to search or look into the pin configuration of that IC. So anyway, when you will be using naman OR gates, you will be needing 7432 for the NAND gates, 7400, for the NOR gates, 7402, so on and so forth. So here we have the 74113, 7404, and X, XNOR, and the XOR. So we have it there. So anyway, this is only for the two inputs. But for example, you will be utilizing, if you will be utilizing a B, like in our example here, you will be utilizing a three input AND gate. So there are also available ICs which have three inputs. So if you will notice in our slide here, the input is only two. So you just search the internet for the number of inputs that you need, and it will give you also the direction on or the item on what IC to use. And again, please take note of the here. How about here? We have three input and gate also. So yeah, you can search the internet what IC to use if you need three input for your design, and you design it the way it is simplified in your design diagram. So here you will be needing siguro sangka IC for three input and gate, and one IC for the OR gate. So and you will wire that one, and that will already serve as your logic diagram. And of course, you need sensors for your input as your input designs. So your input will signal to the IC, and whatever signal the IC will receive, it will check the conditions before it will give you the final output. Well, I think again that is for all for chapter 4.